Okay, good morning, welcome back. I hope you had a good weekend, recovered, enjoyed, whatever. Now we go into the second week. We have we now leave the theme of systematic search through state spaces and behind, but we'll still deal with the game of Schnapsen as our as one of our motivations for doing this. And I guess that many of you have now started to work on the bots and on the programming. And so remember what I talked about last week, namely that I think that the second phase of the game is relatively straightforward, also in the spirit of what we discussed with min-max and alpha-beta pruning and these kind of. So you have an algorithm and it solves the problem. And done. So you know that you have an optimal strategy for playing the game for phase two. But I hope it's also clear that as soon as we have the uncertainty and as soon as we have the complexity of the unknown of the card decks of your opponent, that this very systematic search through the space simply doesn't work anymore, and that we need to come up with new ideas. And the one idea that we're going to look into is next week. It will be to learn from many possible games that one could play. The one that I want to spend now a week beforehand is what we can do with logic and with knowledge and with reasoning. So more symbolic and more explicit representations of expertise that we can put into the game. So some of you might have already played now the Schnapsen game a bit more often. So you see already that there are some things that are in common to most of the games. And the approach that we have looked into so far doesn't take into account at all any of this knowledge that is around there, that is sort of tacit knowledge. And this week we try to look into how we can make this tacit knowledge explicit and how can we use it in building an intelligent agent. So in terms of what I explained at the end of the last lecture on Thursday, we're now looking at agents that have a logical capability, a capability of doing some reasoning over knowledge that is logically represented. In order to do that, I have to get back to the notion of what's logic. And for all of those who have followed the knowledge and data course, that will be sort of a repetition. For the computer scientists, mostly it will be probably a bit longer ago that you heard this, but there won't be any magical things said today. The general idea of a logic is that you deal with information that is partial or imperfect, but that you are able of deriving information that is implicitly modeled by applying some rules and by some commonalities of the structure of the representation formalism. That's the one hand, so we can reason over the imperfectness of the information that we have, but we can also add explicit facts that we as humans have. So information about the environment that we perform in our case, that's the game. And for this, we have a very well-established means, and that is what's called logical formalisms. And that's what we're going to talk about this week. This is also going to be what we will sort of add to the bots, the intelligent agents that we have built last week, or maybe that was a bit incorrect. We, instead of using the systematic search through the search space of the first phase of the game, we now look into the power of sort of human strategies and how much they might help us to win the game. So, as I said, a logic is a formalism that helps us to make to state explicit knowledge about the world, the environment, the agents, and so forth, and then make predictable inference in a sense that basically means that if I give you some knowledge base and the rules or the meaning, the formal meaning of this knowledge base, then you should come up with the same inference as anybody else with the same information. So there is no room for interpretation of what should follow or what shouldn't follow. And that's obviously from a machine perspective very important. So because you can implement it and basically you know exactly what your machine answers. So you give a formal meaning, a formal semantics to your knowledge. And this is what a logic is very powerful for. So what you need in order to do this is a language that is unambiguous, so that you know exactly this is a language in my sentence. This is a sentence in my language. So I need to be able to assign some value to this according to my formal system. So the syntax is a restricted set of possible sentences that I can talk about, and I have to assign a meaning to these symbols. And if you think of how a computer treats this knowledge, for a computer all this stuff is only sort of symbols. It really boils down to combinations of bits in memory. So we need to be aware of the fact that if we say something that a computer is supposed to deal with, the computer has no notion of what this is supposed to mean. And this notion we have to give to the computer, and this is what our formal system and the logic is doing. So the second thing we need, as I said, is a formal semantics. So for all the sentences in our language, we want to assign a value in some other formal system normally. That's how it's done. So we want to formalize the meaning of all the statements, of all the valid statements in my language. And then obviously we are computer scientists. We are not only thinking about what the truth might be, but we also want to be able to calculate the truth. So we want an algorithm that we can apply on one form of machine or the other, so that it helps us to derive these implicit statements automatically, so that it makes these predictable inferences for us. And this is obviously exactly what the agent needs. It needs to have its perception somewhere of facts that are perceivable in the world and in the environment it performs in. It needs to interpret those according to some set of knowledge that it has and that has been formalized according to our logical formalism. And it needs to be able to make decisions on the basis of this. And this is exactly what you are going to do in the second week with your own agents that you implement, where you say, okay, I write down the rules of the game, I write down the situation that my agent is in, and I let the logical mechanisms tell me whether I should make this move or whether I should make this move according to a strategy that you have defined in some formal way, in some explicit declarative way. So in order for an agent, for an intelligent agent to really use this, you need a notion of state. Where am I? What is the information that I have about the information around me? It should be able to perceive the changes of the system by some form of perception or another. And obviously in Schnapsen we deal with a sort of very minimalistic notion of perception, where we simply get the information that our opponent has played a certain card, which is all handled by the machine. So we don't really worry about the perception side of intelligent agents here. Then we need to sort of take into account what has changed by the action of our opponent in the Schnapsen game. And then we can start our reasoning. So what is now the new information that I got from the action of my opponent, so that I can now decide on what to do based on this information. And then in the end, you will see that the action that we can take can be just a logical reasoning step in one of the formalisms that we know. So the example that is in the reader, and that comes from this beautiful AI book, is a very simple game scenario. It's the Wampus World. And the Wampus World is a game where I, as an agent, start in it's a 4x4 maze kind of thing. I'm an agent, and I want to come to the piece of gold that's hidden somewhere. And so the task is to move either to the left, to the right, or to the left, up or down. I have to be careful that I don't bump into the Wumpus because he's horrible. And I have to be careful that I don't fall in the pit. So these are the two dangers. I can get some extra points if I feel the glitter of the gold. I can, and I will be warned by the pits, because the pits, from the pits come a breeze. So on the adjacent fields of the pit, you feel a breeze. And on the adjacent fields of the Wumpus, you can smell a stench. So we have a certain goal, namely that we want to go from the position that we're in to the state where we found the gold. We get some reward for the gold, and we have some cost functions. So this is sort of the traditional definition of the agent framework, that you sort of behave, that you have to behave somewhere in the environment to derive to a task, and then you get some reward for it. We have an environment with formally specified properties, so that makes it easy for us to formalize it properly. We don't need this abstraction step in the middle. And it has some properties such as squares adjacent to Wumpus are smelly, squares adjacent to the pits are breezy. That's what I already told you. And then we have more information. Glitter is if there is gold in the same square. There are some actions that can shoot to kill the Wumpus. So you could implement this in some simple kind of game engine, and then you can see that it's an idea that sort of is very similar to many of the computer games that you face now. You have rooms where you move from one room to the other, and you face some enemies, and you have to take some action. And it's a very simplified abstraction, of course, but the kind of gives some idea of what kind of actions you might have to do and how you might get to these actions. We have some sensors, breeze, glitter, and smell, and they won't take any sort of big role in the rest of the story, but it just shows you in that sense that this is just a continuation of what we did last time, as one of the agents performing in an environment, trying to perform rationally to maximize an outcome of finding the gold with as few steps as possible, and so forth. But now, and of course the problem is that it's a local observation. So when I'm in position 1-1, I don't have any perceptions. So I only perceive something when I go to 1-2, because then I feel the breeze. But then I still don't know what's left and right and above. And if I now move to the right, I fall in the pit. So that would be a stupid thing. So I need to do some reasoning to avoid falling into the pit. And it's exactly the reasoning that helps me find the gold, but avoids the glitter, avoids the pit and the Wumpus. That we need the logical capabilities for, the reasoning for. So again, one step back to what we discussed on Thursday. It's non-fully observable for the agent, because the agent only gets information of where it stands in the 4x4 square. And it only knows what happens in the locally. It's deterministic because whatever you do, you know exactly in which position when you take an action, you always end up in the same position. It's not you can't take the same action 3 times and you get to 3 different positions. That's impossible. It's a static environment, because the Wumpus somehow belongs to the environment and doesn't do anything. It has no own interests or intelligence. It doesn't behave. So we treat it here as a single player game. It's discrete, so every step you have a time, sort of clock, and every step that you can't do an action in between each of those steps. And it's a single agent thing. Because, as I said, we treat the Wumpus in a way as part of the environment with no interest. So in a way, this is an online search problem. So you go to some position, you try to evaluate all the different options, and you try to possibly look ahead if you can, but you can't because you don't have that much information. So you have to reevaluate your search every step you make, and then you make a new decision. You have to reapply your search algorithms. And in a way, this is very similar to what we're going to do in the Schnapsen, because you will have to reevaluate your position every time you've played a card. You try to look ahead a bit in the first phase, but it doesn't really make that much sense. So you need then in the next step to reevaluate what you have, how the situation has changed, because you get more information and so forth. So now the task is to explore this Wumpus world. So this is an abstract representation now. Our agent is in position 1-1. And we know that it's okay, because otherwise it would have been already game over. And now, because there is no percept here, so we don't smell anything and we can't feel a breeze, we can derive by some logical reasoning, knowing the rules, that 2.1 and 1.2 are both okay. So that I can go there without having the risk of falling into a pit or being eaten by the Wumpus. So it's an action I can take is to go either to the right to 2.1 or an action to 1.2. So the Wumpus would, the agent would take a random decision, and in this case it goes to the right to the position 2.1. That's the first step. And now there is something happening, because now we feel that there is a breeze, so we realize the B. We know that the position is okay. We had already established that. But now there is a problem that in either of those places, in 2.2 or in 3.1, there could be a pit, because we feel the breeze. So now we need to make the decision, what should we do? We could take the risk and say, okay, we go 50-50 chance, we go right, and then we start the game again. But we can also do some reasoning and say, okay, we have explored 2.1, there is the risk of losing, so let's go back and let's explore the other part of the online search trace. So instead of going here, because I know that there is the risk that there might be a pit here or a pit here, the agent would decide to go back. And then the agent would decide to go up to position 1.2. And now comes a sort of the clever bit of reasoning that it does, namely that there is a smell in this position. So there will be the Wumpus somewhere. But now the reasoning is that this place is okay, 2.2 is okay, because if the Wumpus would have been there, I would have had the smell here. And if it would be a pit, I would feel the breeze here. Yeah? So by simple reasoning over the states, over the possible percepts that I have felt, and that the information that I have, I can now derive the fact that because of the lack of breeze in 1.2, and because of the lack of smell in 2.1, 2.2 is a safe state. So the agent can now move from 1.2 to 2.2 and then go up to the gold and find the gold. So there was no way, if we had played this in the naive way, that we would have known that this is a safe state. So we needed this logical reasoning over all possibilities of the world to tell us that 2.2 is a safe state. So here this is an example of how this logical reasoning helps us to maneuver in a world where we have imperfect information, where there's never explicitly stated that this is a safe state, but that we can derive it anyway. Yeah? So this, if you look at the slides later, it will show you that by these arguments, you can win by maneuvering through the safe state by doing some inference, some logical reasoning. So in a way, Wumpus is an exploration game. And all we need is some basic information about the different states, and we look at those states and we get additional information in whether they are safe from being a pit or from a Wumpus, and we just get this information from basic reasoning. We do the same with the card game, our Schnapsen game, where we also have some kind of online exploration, as I said, and where we really want this explicit definition of heuristics in a way. This is now the goal, really, and help us with logic as a language to put in the knowledge that you need in order to be able to maneuver through the card game to the states where you think gives me the highest chances. And in this case, the Wumpus world was really clear, very clear cut. The card game Schnapsen will be a little bit less because there is no states that are really absolutely incorrect. Like here, there would be an incorrect state, namely you go to a place where there is a pit, you fall in the pit, you're dead. We don't have that in Schnapsen, but we can still add some strategy to the game where we say, okay, if you have a wedding, play it. Or if you have a king and a queen, don't play the king and don't declare the marriage or something. So human knowledge, we'll see later how this can be included to the game so that we can make decisions. Yeah?
Let's say
yeah.
You have a result, so you have to take the risk. Is it valid to just sometimes take a guess like this?
Absolutely, yeah. So logical agents can't perform miracles. So if there is a lack of information, then they can't do anything. So in this case, the magic, I would say, was that the information that 2.2 was safe is there. It's just not written anywhere, and you can't measure it. You can't perceive it. So you can only know it by reasoning. Yeah. But there are cases where there is no information, where you don't have the information, and then of course you need to do some guessing. So that would be something that comes back in the implementation of Schnapsen. The way I propose it to do in this week, that you have some strategies, always play the highest cards, or if you have a low card, play the low, that still is powerful, play the low card. And if none of your strategies work, or you don't have a strategy for the deck of cards that you have to play random. I mean, there's nothing else we can do. But that's exactly what I as a human do. So if I don't have a strategy that I can apply, I just play a card and see what my daughter does. So that's fair enough. So logic won't help you sort of solve all the problems. Only those where you can really derive something explicitly that is useful for your game. So a logic, we need logics, and the core thing really about a logic is that you can make facts explicit that are only implicitly modeled about your domain and your perceptions that you can collect. So in a way, we need some mechanisms, some algorithms later to produce new facts that are valid according to the rules of the game. So what's a logic? I already said it's a system for me that consists of a syntactic description of all the valid sentences, syntactically valid sentences. So which expressions are legal? Legal is a better word than valid because validity has also some meaning in the semantics of the word. So which expressions are legally well-formed sentences? So which are the expressions that I want to give to a computer and the computer tells me, yes, I know what this means. Yeah? And anything that I give it that does not adhere to these criteria, it simply says, okay, I don't know what I should do with this. For all the sentences that are legal according to my syntax, it should also give me an answer what the meaning is. Then the semantics I was already talking about is a formalism that tells me what the legal expression is supposed to mean. And it gives me all a meaning for all the sentences with respect to some kind of interpretation of them in the world. And based on these interpretations, I then can make inferences. I'll get to that in a minute. And then the last thing, that's something we look into more in detail on Wednesday, is a calculus. How can we translate this meaning into something actionable where a computer can determine the meaning for these legal expressions automatically? And this is an example for such a formal language, which doesn't look like really like a traditional logic, but it's a sort of a simple language of arithmetics. And if you have been in knowledge and data, you've seen this example already. So the idea is that you define sentences that basically have on the left-hand side have some terms which are meant to be interpreted later to be numbers, natural numbers, and those can be simply variables, or they can be numbers, and basically that's it. You can sort of lift those numbers if you combine them with some mathematical operators. So if you take one of those and you take one of those, you can also combine them to a legally formed term that is supposed to represent a number as well. And you can do the same for, you can also use the variables, that's also acceptable. So these are supposed later to be interpreted as natural numbers. And then if we want some notion of truth, we can add something that takes those terms on the one side and on the other side and compares those terms once they are interpreted. So this allows us to write down things like x plus 3 minus 2 is always smaller than x plus 4. Yeah? So this would be now a valid sentence. I didn't talk about the parentheses. You have to take care of the parentheses, that you do it in a proper way. It's a sort of just an example, but we know that we can somehow assign a value to this left-hand side. We can assign a value in the natural languages to the right-hand side, and then we can assign a value, a truth value now, to this inequality. And if we have variables in our language, we need to somehow deal with these variables. So you would say, now that when we move to what does it mean, such a sentence here, we have to think of what could the x mean. And basically assigning a value to these formulae now works by interpretations. And these interpretations mean what value could x take, and depending on what value x can take, will this sentence be true or not? So basically, suppose I assign the value 1 to x, I can now assign a value to this formula, and this value to this formula would be 4 minus 2 is smaller than 5, which is true. Yes? So basically, this assignment makes this formula true. I've now moved from the syntax, where I just showed you how a means of writing down formulae, to the semantics, where I now assign a meaning depending on the assignment of values to the variables, basically. And now I can try this for different worlds, as it's also sometimes called. So one world would be where x is 1, another world would be where x is 400. And if I apply this, I again get 401 is smaller than 404. So you see again, for this choice of x, the formula is evaluated to be true. Now, you understand what I'm doing, because whatever value x you choose, in this case, this formula is true. So this is a very special formula. It's a formula that's always true, independent of the choice of x. And this gives me a special notion. So this would be a valid formula. It's valid. It's always true, independent of the choice of model. Yeah. So you see that I can build certain formulae, and if this formula is legally defined, then I can assign a value depending on the choice of the world. So if x is 7 and y is 1, then this inequality is true. If x plus 2 is smaller than x plus 3 is a formula that's true in all the worlds, so it's like this one that I explained here. And there are also ones that are false in a specific world or false all the time. So these are sort of special cases that we'll see later that are interesting in a logical formalism, and I will introduce them formally for a specific logic, as you will guess in a minute. And finally, you also want to calculate whether a formula is true or whether a formula is valid. And to prove that this formula, for example, would be valid, we would have a calculus such as algebra, and we would apply algebraic algorithms that would allow us to reduce this formula to, and now I'm sort of to smaller x is smaller than this was plus 1, we have to go minus 1. So it would reduce this formula to this, and we can show by, we know that in the natural numbers this formula is true, so we have reduced this one by algebraic reasoning to something we know is universally true. So that would be our rule-based calculus. For the kind of information that we are dealing with in Schnapsen and in the Wampus world, we don't need to look that much into the arithmetic, though we'll come back to that tomorrow probably. But we look at logics that allow us to talk about propositions and predicates and relations between objects in the world. And for some of you, this is the third time that we talk about propositional logic. For some of you, it's the second time. So I hope I can be relatively quick. But this is a really very nice formalism because it's very well understood. It's very simple. It has some very natural operators that are very close to how we as humans deal with the world and the environment. But it's still very powerful. It has very efficient algorithms, as you see. And therefore, it is useful and it's worth looking again. And I think what you haven't done is to look into first-order logic and propositional logic and how you can really use this to model complex problems such as strategies in Schnapsen. And this is what I plan to do tomorrow with you. So to look into how we can apply propositional logic and first-order logic, what I'm going to talk about later, in a practical applications, how you can use a reasoner to tell you whether you should play a certain card or not, like you would use a reasoner to tell you don't go to pit to place 1-2 or 2-2 because there is a pit. So the syntax of propositional logic is very simple. You just have a countable set of propositional symbols, and they can be interpreted to anything which is true or false. So it can be true or false. So it's raining, it's early in the morning, it's late, this is a chair, this is a table, this is a chair as well. So whatever you can say in these atomic way where you think this could be true or false, this is what you would normally model in a propositional variable. And then you have a set of operators which are assigned a form of semantics, and that is the negation. So this is not a chair. One would probably say you can combine formulas conjunctively. This has to be both. It has to both rain and be -5 degrees before it starts snowing. You have a disjunction where you say it could be it could be either warm or I would have or the sun should be shining in order for me to go swimming. The interpretation of this, as we later see, is is that it's either the one or the other or both. So it's not an exclusive or in propositional logic. Then you have an implication. So if the weather is nice, I go for a swim, or an equivalence. So that's an implication in both directions. Whenever the weather is nice, I go swimming. So you can also derive that when you I go swimming if and only if the weather is nice. So whenever I go swimming, you can also derive that the weather is nice, and vice versa. So these is the language that we use to model exactly the things that I've just talked about. So what's the semantics that you would assign to those sentences? And that is now a bit more complicated than maybe seems necessary, but truth is really difficult. So if you say it's true that it's snowing outside, then sort of how do you what does it mean? You need to relate some strings in the world to some notion outside. And philosophers have really tried for hundreds of years to really come up with a consistent notion. And the best notion I think people came up with is so-called Tarski semantics. So Alfred Tarski was the person who invented this, to define truth depending on all possible interpretations. So it doesn't really matter whether you relate snow outside to the fact that it's really snowing, because this is something we can't do that easily. But we can only derive facts whatever way we interpret the notion of it snowing, it's always true. So we identify truth depending on the notion of a model or the notion of an interpretation as I gave it here. So this statement is true because it is true, is valid because it is true in all the interpretations that I could give to the variable x. So the definitions here are, we have a set of interpretations of the world, and these are formal interpretations such as I give the value 1 to the variable x. And then we call a model any interpretation that satisfies the axioms of my knowledge base. So M is a model of a sentence alpha, here I start with the sentence, but I do it for all the sentences in my knowledge base. So M is a model of a sentence if M adheres to the constraints of alpha. So basically, if you interpret alpha with the constraints of the interpretation, then you get a true sentence. And then all the interpretations that do this, they are called the models of the knowledge base. And once I have this notion of models, then all the formal interpretations that are sort of good with the axioms in my knowledge base, then I can define notions that are closer to truth than anything else I would think exists. And that in particular is the notion of entailment, where I say I have knowledge in my knowledge base, and I can define exactly which of the things are logically true with respect to this knowledge base. And the definition is formally that a knowledge base entails a sentence alpha, if and only if alpha holds in all the worlds where the knowledge base is true. And then based on the models, we can really unambiguously define this notion of predictable inference, because this is the semantics of what follows logically, what is entailed. That tells us exactly which of the formulas we know are true with respect to the knowledge base. So let's see before we have a break, let's see how this looks in the Wumpus world. And remember the situation where the agent has just moved to the to place 1, 2, and it has noted that there is a breeze. So now there are the options that here, or here would be a pit. So we have to do this sort of understand what's happening. And the question is, where should it go? Should it go here, should it go here, or should it go here? So I only look at the possible interpretations of what could the situations be for these 5 squares in the 4x4 matrix. So these are all possibilities that could be there. So we know that there is nothing here. We know that there is a stench here. So these are the two things that are true in all these interpretations. These are sort of facts. We know of these facts. But the rest we don't know yet. So here could be a pit, or there is no pit. We believe that we know. We know it by reasoning. We'll see that later. But in principle, we don't know it yet. We have to derive it. So let's look at all the possibilities. So there could be a pit into 1. There could be a pit into 1. These would be these 4 situations. Or there is no pit in these situations. There could be a pit here. We also have 4 possibilities here where there is a pit in 3.1 or 1.3, sorry. And the same we have 4 situations with a pit here and 4 situations with a pit here. So these are all the possible interpretations of whether there is a pit or not. Now, some of them are consistent with respect to our knowledge base. Namely, the knowledge base tells us that if you have a breeze, then there must be an adjacent pit. So let's look at those that are consistent with these rules and observations that we have. So this one is because it has a pit here and here, so that's valid. So it will smell here. This one is also because there is a pit here next to the smell, and the same here. This one has a smell, and there is a pit next to it. So these 4 are consistent. We also know that here was no breeze. Oh, sorry, I talk about smell, but I meant breeze. So it's so there is no breeze here, so there can't be a pit here. Same here, no breeze here, so there can't be a pit here. So these 3 are consistent with the rules of the game and the information that I have already. These are not, because I didn't have any perception here, so there can't be a pit here. I know that this violates my constraint. The same here. This violates the constraint that there can't be an adjacent pit if I don't have a breeze. This one is inconsistent because there should be a pit somewhere around. This one is inconsistent because I have the pit. I should have felt a breeze here. And the same here. I should have felt a breeze here. So these 3 worlds, these 3 interpretations of the world are consistent with my knowledge base, and these 5 are not. Yeah, is that clear?
The bottom left one and the one above that, shouldn't they have the breeze next to the top? Yeah.
Yeah? They should have a breeze, but I don't know yet, because I haven't been there. Yeah? So based on the information that I have, this is what I can derive. So now I can say that so basically these 3 red things, they are my models. Yeah? So now the definition of entailment was that if something is true in all the models of the knowledge base. So remember, this was the definition. So the knowledge base entails something if here we are, if it holds in all the worlds where the knowledge base is true. So now let's look at our model space again, our interpretations, and the question whether the space 1.2 is safe. Yeah? Basically, where here, in this situation, we don't have a pit. And basically now, if we look at all the interpretations of the world, then we see that here is safe, here is safe, here is safe, and here is safe. Yeah? So we have this yellow line about these 4 interpretations that are valid with respect to this information of alpha 1.2 is safe. Yeah? And what we see is that in all the states, all the models, so these 3, this is true. So basically the definition is the same as to say the set of models of the knowledge base is a subset of the set of models of my assumption. If you think about it, it's easy to see. Yeah. So by simply looking at all the possible models in this situation, what's called model checking, we can prove that the knowledge base entails the formula that 1.2 is safe. So exactly the reasoning that we did beforehand in the sort of informal way when the agent was moving from left to right and up and down and explained that it could go to 1.2 is something that you can formally check if you just represent the rules of the game and the information about the game state you're in. If you try the same for the information whether 2.2 is safe, you just look at all the worlds in which 2.2 is safe. So that would be the ones where here is no pit, there is no pit, there is no pit, and there is no pit. So we talk about these four, yeah? But now, the knowledge base, the models of the knowledge base are not a subset of the models of this assumption. So there is a model of the knowledge base in which the assumption is not true. And that violates this definition of entailment. So basically we get the definition that the knowledge base does not entail this statement that 2.2 is true. So if you are an agent and you have represented the rules of the game, you just have to ask a logical reasoner, is 2.2 is safe entailed by my knowledge or not? And if it is, you can go there. If it is not, you cannot go there. So that's the power of logical reasoning. If you manage to represent the rules of the games properly in a logical formalism. And I think that's a good moment for a break. Shall we meet again at 12? So have the break a little bit shorter, and I try not to overrun instead. Yeah, or finish earlier if possible. Can you?